Okay, AP Calcers, we're moving on into section 2.3, a section that I warned you would be one of the shortest and fastest ones that we were going to do all year. In fact, I have so little regard and respect for this section, I never even bothered to type up my notes. What's the point, is what I figured. It's going to be 4 slides and we're done. So basic limit laws are some of the laws and the rules that we're going to be using to move forward now to actually start evaluating real limits, as we talked about doing in section 2.2, albeit with more complicated functions. But as I said earlier, this is a section where the 4 things that we're going to learn here are going to feel so obvious to you guys that you almost would have done these things instinctively even if you hadn't been told that you could, which is technically a bad thing, but let's run through it. So, a few laws we're going to talk about. The first one right here is the sum law for limits, not to be confused with the sum law for derivatives or the sum law for integrals that we're going to be doing later on in this year. But the sum law for limits, everybody, is written in this manner right here. But the way we're going to learn to say this and think about it would be that if we are taking the limit of a sum, the limit as x approaches a of the sum, or the difference actually, you'll notice the minus there on the bottom, of 2 individual functions, f of x and g of x. And the way we're going to read this out loud, everybody, is that the limit of a sum is equal to the sum of the limits. I'll say that again. The limit of a sum is equal to the sum of 2 individual limits, or the difference. So what we're going to do, and I really hate to say this, guys, although it's what I think you're going to think of anyway, you're kind of allowed to distribute that limit inside the set of parentheses. Forgive me, math gods, I know not what I say. We're not distributing here, guys, because you can only distribute a number and a limit is an operation. But the sum law for limits says that the limit of a sum is equal to the limit as x approaches a of the first function, which we've called f of x, plus or minus the same limit as x approaches the same value of the second function, which is g of x. So that's what we mean when we say the limit of a sum is equal to the sum of the individual limits. And we're really not distributing, but that's how a lot of people like to think about it. Now, this one is not overly consequential, I am sorry to say. The case we would use it in would be a spot, probably something like this, that you guys wouldn't even look at and think, oh gee, this expression right here, 5x squared minus 7x, is actually the difference of 2 individual functions. Most of us would probably look at that as one big function, a binomial, 5x squared minus 7x. But it could be treated as such in 2 different ways. So let me get rid of all the junk that I had here. And I'm going to write out a step here, guys, that I would never write again other than to prove my point here. That if we were to think of 5x squared being the first function, and then 7x being the second function, we could rewrite this now as the limit as x approaches 2 of 5x squared, full stop, minus the limit as x approaches 2 of 7x, and stop that one right there. So we're really just trying to build on some of these fundamental ideas that we were talking about earlier on in the chapter. But again, from here, this is going to be pretty easy to work out. Now, one of the things I'm always worried about that the book and your author don't state as specifically as they probably should is that when it comes to evaluating a limit, we're looking for the value that this function right here approaches as x approaches 2. And I said in great detail in section 2.2, we don't actually care what happens when x gets to 2. We only care about what happens when x approaches 2. So in certain cases, making the table of values or looking at the graph is going to be maybe the more important way to handle this. But the important thing to take away, this is what we need to know, everybody, is that if the function you are dealing with, in this case 5x squared, is continuous at this particular value of x, then we can simply do direct substitution. And that happens in both of these cases, guys. 5x squared and 7x are both continuous functions for all real numbers. So again, I'm showing more work here than I need to, but we can simply, in this case, substitute the 2 in for the x's here and make this 5 times 2 squared minus 7 times 2. That's going to get us a 20 here for the first term, a 14 for the second, and we're going to end up with an answer to this limit problem of 6. Now, with all that moving forward, you might have caught what I said there just a second ago and realized how silly it was to ever go to this step in the first place. If this function right here was continuous at x equals 2, you could have just put the 2 in directly for those x's and gotten this answer much faster. But having talked about the sum and difference law, it allows us to do what otherwise would have simply been an assumption that we then could have substituted that value in there and made it 2 different functions. So not one that you need to waste your time trying to memorize or really even to write down. It just allows you to evaluate a limit term by term in a polynomial function. So that one was pretty straightforward. Next one. The constant multiple law. And this is another law, much like the sum and difference law, that shows up 2 more times during the course of the year. Again, a second time with derivatives that we'll do in Chapter 3, and a third time with integrals, which we will do in Chapter 5, probably in January. And in each of those cases, I really should have had a set of brackets here. What we're doing is, in this case, taking a limit of the product of a constant value, c, multiplied by a function. And the way that you know that c is a constant is not just because we use the letter c. It's because this letter used right here, x, that's the variable of the function. So this is a limit as x is approaching some arbitrary constant value of a, and since x is the variable, we know that f of x is the variable function. Okay, so the constant multiple rule simply says, and it takes advantage of something we had talked about earlier here, I think in section 2.2, that a limit as x approaches a of a constant, well, nothing really happens. You're just going to end up with the value of the constant itself because a constant function is unaffected by the value of x because it has no x in it. So all we're going to do here, guys, is pull that constant out in front and now multiply it by the same limit, the limit as x approaches a, but just of the variable function itself, which in this case is just f of x. So the constant multiple law, and again, we'll see the same thing with derivatives and integrals later in the year, says you can take that constant and simply pull it out in front of the limit because the limit has nothing to do with the constant. The constant value always remains the same, hence the word constant, which is the opposite of the word variable. A variable, its value can change, but a constant must always remain the same. So, does this one have a ton of practical application? Not a lot to it, but the one example I wanted to show you right now would be a simple example that looks like this. The limit as x approaches 5 of something ugly, but a factored expression like -6/7 multiplied by the quantity of x squared minus 5x plus 1. And if you didn't know this particular law, it might be tempting for you to say, all right, that's the function right there in the red brackets that we are taking the limit of, and you might be tempted, everybody, to take that -6/7 and distribute it back into the trinomial and then apply the limit as x approaches 5 after the fact. Well, I made this one difficult and ugly on purpose just to kind of discourage you from doing that. The constant multiple rule says that rather than put the -6/7 back in there, we can go exactly the opposite route, and we can take this constant, because it has no x's in it, and pull it all the way out in front and make it a coefficient of that limit. So this would be equal to our constant, which is -6/7, multiplied by the limit as x approaches 5 of the trinomial x squared minus 5x plus 1. And then we can just worry about the 6/7 later. We can just kick the can down the road, okay? All right, so what do we have now, guys? This now becomes a -6/7 multiplied by, and once again, this is a continuous function. It's a quadratic, so it has no problems with its domain, no jumps or holes or asymptotes, so we can simply put the 5 in there and see what we get. 5 squared gets you 25, minus 25, that's convenient, that was 0, and plus 1 gets us a 1 for the limit as x approaches 5 of x squared minus 5x plus 1. Again, let me say one more time, the only reason we're allowed to actually put the 5 directly in there for the x is because this function here is continuous at x equals 5. But if we had any of the multiple problems that can occur with continuity, we'd have to find a more complex way of dealing with that limit. And anyway, we were just about done, everybody. Now, we take this constant value of negative 6/7, we multiply it by the limit of that function as x approaches 5, which is 1, and we just end up with an answer then, guys, of negative 6/7. And I wanted to do one more problem with you here in this section, just because this one bothers people a little bit. And I think one of these shows up on your homework, so I thought I would try to head off a question here before it got asked. Taking a limit as x approaches 3 of 4y plus 6 multiplied by 2x minus 4. Now this doesn't look exactly like the last problem, whereas in the last one we clearly had a constant out in front of the function of negative 6/7. Now we don't. But what I do want you guys to get in the habit of looking for is this fundamental idea right here. If we look at the limit, the variable of this limit problem is x. That means that this expression right here, that factor of 2x minus 4, is impacted by the limit as x approaches 3. But the value of x has absolutely no bearing whatsoever on the value of 4y plus 6. There's no x at all in that first binomial factor. And so even though it's not technically a constant, it is a coefficient unaffected by the limit, so we can still treat it like a constant and bring that first binomial factor all the way out in front and make that 4y plus 6 multiplied by the limit as x approaches 3 of 2x minus 4. So then we can go ahead and evaluate this. A 4y plus 6 is now going to get multiplied by, well, 2x minus 4 is a continuous function everywhere, so go ahead and put the 3 in there. 2 times 3 minus 4 is going to get us 2. And then at that point, I should clarify, guys, that this is big kid math. And if you wanted to leave your answer as 2 times the quantity 4y plus 6, you'd get full credit for that. Even though right now you're in no man's land, you're not fully factored and you're not fully expanded. So I don't love this answer, but you would get credit for it. I would say either distribute the 2 in there all the way and come up with an 8y plus 12, or you could have continued to factor another 2 out of here and here and then multiplied that 2 by this 2 to get you a fully factored version of 4 times 2y plus 3. So either one of those answers would have been perfectly acceptable. Really, so would that one as well. The AP graders are going to tell us all year long that your answers do not need to be fully simplified in order to get full credit. As long as they are algebraically sound, you're good to go. So 3 different versions of this same answer. Okay, we're already spending more time here than we need to. The product law. I do want to point out that there is a product law for derivatives in Chapter 3 that we're going to learn, but it is nowhere near as simple as the product law for limits. There's not really a product law for integrals, everybody, but we'll get to that in a few months. So the product law for limits says really the same thing that the sum law for limits says. This one, if we read it in a certain way, says that the limit of a product is equal to the product of 2 individual limits. So again, I hate to use the word, but we're kind of distributing here. We're taking the limit as x approaches a of the first factor, which is f of x, and multiplying that limit now by the limit as x approaches a of the second function, which is g of x. This will not work with derivatives when we get to it in Chapter 3, but for now, guys, let's remember it that way. The limit of a product is equal to the product of two individual limits, and that's what's going on here. So what does that do for us, everybody? That allows us to take an ugly problem like this. The limit as x approaches -2 of the product of two quadratic trinomials. So there would be like f of x and there would be g of x. And without this law, oh, this would be bad. We would need to put a set of brackets around all of this, and now we'd have to pretend like we're back in Algebra 1 and actually multiply out two trinomials, which would not be fun. It would start with a 35x to the fourth. It would end with a +2, but we probably would expect, what, 5 terms from that mess. We can do it, but it's like decimal long division. Come on, we're adults now. We don't have to do stuff like that. So instead, we can use the product rule that says that the limit of a product can be broken down into the product of two individual limits. So this is the limit as x approaches -2 of 5x squared minus 3x plus 2. And once we find that limit, we can multiply that by the limit as x approaches -2 of our g of x, which is 7x squared minus x plus 1. And again, because these two functions are quadratic, they have no problems with their domain whatsoever. They are continuous for all real numbers, and that means that we can simply plug and chug this -2 here, guys, and find out what these limits are. So let's see what we can do mentally, guys. -2 squared is 4 times 5 is going to be 20. That is going to be a +6 and a +2. So that first limit right there sounds like it's going to be 28. We would multiply that times the limit now for the second part. So once again, -2 squared is 4 times 7 is 28. Now we're at +2 right there, so we're at 30, and +1 is going to get us 31. And I'm not sure why I felt the need to give you something really ugly like this, but apparently I did. So 28 times 31, I don't know, what do you got here? 28 times 31, it's around 900, 868. We'll run with that. Okay, I am confident, everybody, if we had taken the time to do trinomial times trinomial right here, and we had come up with that big, messy, what did I say, 5-term polynomial right there, it would be a quartic, and then we had plugged a -2 into that quartic function, we would have ended up with 868. But I don't really think it's worth our time to go back and verify that. And the last law here, everybody, for the day, I bet you can guess. If number 3 was the product law, then you could probably guess that what's coming next is called the quotient law. And if the product law tells us, everybody, that the limit of a product is equal to the product of the individual limits, then I think it stands to reason that the quotient law is going to tell us that the limit of a quotient is equal to the quotient of two individual limits. This would be the limit as x approaches a of f of x up here on top divided by the limit as x approaches a of g of x down here on the bottom. And I certainly hope that no one is tempted to say, hey, I've got a limit as x approaches a on top and a limit of x approaches a on bottom, and they simply cancel each other out. That ridiculous bit of reasoning right there, come on guys, would only be true if these were numerical factors that were being multiplied by the numerator and the denominator. But a limit as x approaches a isn't a number, guys. It's not a constant and it's not a variable, it's an operation. So what I just did is as silly as people trying to divide by a logarithm on both sides of an equation. It is not something that dignified people like ourselves are going to try to do. Now, the one thing we've got to be careful of with quotients that we didn't have to worry about with sums or differences or products, I think you guys know where we're going with this. With everything you've learned about addition over your entire life, addition works with all real numbers. Same thing with subtraction and same thing with multiplication. But the one tricky thing about division, everybody, the one number you are not allowed to have within a division problem because it makes the entire world crumble and burn is if you end up with a 0 in the denominator of your fraction or a 0 for your divisor, everybody. We cannot have this denominator here on the right equal to 0. So you do have to throw in this little caveat, this little asterisk right here that says, whoa, 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 this only works if the denominator, the limit as x approaches a of g of x, does not equal 0. As long as that doesn't happen, then yeah, this quotient law is legit and it'll work in all cases. Guys, I wasn't even going to do an example with you, and no kidding, that's all she wrote. So those are the 4 limit laws that you guys need to know for section 2.3. I think you're going to plow through this homework very, very quickly, and this will be like the pioneers crossing the Great Plains of Nebraska, everybody, before they got to the Rocky Mountains. So bad stuff is coming in the future, but for now it's pretty smooth sailing if we can just avoid dysentery. All right, good luck everybody, and let me know if you guys have any questions.